Alright, so we are looking at sequences, and this is not the last unit, but it's like the big, last main thing, because after this we're also going to look at doing all the calculus in different coordinate systems, which will be fun. Yeah, so sequences. We're looking at some definitions, we're going to ask the question, does this converge or diverge? And then we're going to look at factorial, which is very exciting. And then we'll talk about the squeeze theorem, monotonicity, and boundedness, and then what that implies. So a sequence is a function whose domain is the positive integers. So the inputs for a sequence are the positive integers, which is blackboard bold z with a little positive superscript. So that's the fancy math way of saying positive integers. So what are the first few terms for these sequences? We got a sub n, b sub n, and c sub n. So think about it a little bit, and then we will talk about it. What are the first few terms for each of these? So for a sub n, we have 3 plus this -1 that's raised to the nth power, so that the value here is going to alternate between positive and -1, and then the 3 is staying 3. So if we plug in our first positive integer of 1, then we'll get 3 minus 1, we'll get 3 minus 1, so that's 2, and then we'll get 3 plus 1, so that's 4, and then it'll be 2, 4, and so on. For b, what are we going to get? Well, if you plug in 1, you get 1 over 1 minus 2. What is that? That's -1. And then you get 2 over 1 minus 2 times 2, which is 2 over -3. And so what's next? You get 3 over 1 minus 2 times 3. So what's that? 3 over -5. And so we got -1, -2/3, -3/5, and so on. And then for c, we're plugging in 1 to anywhere we see n. So you got 1 over 2 to the first power minus 1, and that's 1 over 1, which is 1. And then you get 2 to the second power, 2 squared minus 1. So what's that? 4 over 3. And then if we plug in 3 for n, we get 3 squared over 2 cubed minus 1, 9 over 7. Whoa. And then if we plug in 4 squared over 2 to the 4th minus 1, 4 squared is 16, 2 to the 4th is also 16 minus 1 is 15. So we got, starting at 1, then we go to 4/3, 9/7, 16/15. Another vocab is recursively defined sequences. So that's where, for example, we're just going to choose another sequence name. We're going to say d sub n. That's going to be defined as our first value is 25. So we got 25 first. And then our next value, so our d sub n plus 1, is our current d sub n minus 5. So we're going to take 25, subtract 5 from it, and so our next thing is 20. And then we're going to subtract 5 again, so our next term is 15, subtract 5 again, and you're going to get 10, and so on. So that's recursively defined sequences. There are other very cool recursively defined sequences. One of them is called the Fibonacci sequence. It starts 1, and then you take the previous term and add it, the previous 2 terms and add them together. So 1 plus 1 is 2, and then 2 plus 1 is 3, 3 plus 2 is 5, 3 plus 5 is 8, and so on. And it's cool with this that if you start drawing squares that are of unit size of like what's in the Fibonacci, in the sequence, the Fibonacci sequence. So you just start drawing like, oh, that's a side length of 3, there's a side length of 5 square, there's a side length of 8 square, and you do that in a spiral, then you can get the golden spiral, which shows up in a lot of things, including nautilus shells. It's very cool. So a sequence can have a limit, and the limit of your sequence is going to be a number, because all limits are numbers. So we're going to let L be a real number. The limit of our sequence is L, written as the limit as n goes to infinity of a sub n goes to equals L, if for each epsilon, so epsilon is a change in your y value, there exists an m greater than 0, so a certain x value, such that for any of your a sub n terms minus your L, your limit, so we make this epsilon sized, or this 2 epsilon sized band, because that's the height of that band is 2 epsilon. As long as you're picking a number big enough, you're going to get close, like arbitrarily close to your number L. And if we do have a limit for our sequence, then we say that sequence converges. So I promised that convergence would come up again. So I didn't promise that, but I said that. So our sequence converges to the number that we're looking at here. And if the limit for our sequence doesn't exist, then we say that that sequence diverges. So we have convergence and divergence with sequences, just like we have convergence or divergence for improper integrals, which is pretty cool. So if we have a limit to a sequence, then we have L as a real number, and we can have the limit of a sequence with this function, L, and that's going to be also valid for our function with n as inputs, where n is positive integers. That's what that's saying. So if we have a function, we can also think about it in terms of the sequence, and that those limits are going to be the same. So find the limit of the sequence whose nth term is this. That's the same as saying limit as n approaches infinity of 1 plus 1 over n to the n power equals what? What number is that? And maybe you remember, maybe you don't, but this is one of our special limits, and that's going to be Euler's number. And then we have properties. Properties are pretty much, these are just showing us that numbers behave the way that we think they will, which is very exciting, but also very reliable, which is nice. So we have this limit number and this other limit number. Then when we take the sum of them, we're going to get the sum. Or if you're taking the difference of these two sequences, then we're going to get the difference of those two numbers. If you're taking the product of those two sequences, and your limit as n approaches infinity, so your n behavior of these sequences, you're going to get the product of their numbers. Scalar multiplication works the way that we think it will, and division works the way that we think it will, which is essentially saying that we have this, but with the reciprocal. So this is just making sure that we don't have a 0 in our denominator, because that will give you something that is undefined. So the question is, does our sequence converge or diverge? And for each of these, I think we can figure it out. So if we're thinking about for A, we had pretty much, like, everything was alternating between 2 and 4. And so as we were going up in our ends, we're just alternating, boom, 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 between 2 and 4, because it's 3 plus or minus 1. So this is going to diverge because we're not getting a number. So this diverges. For B, what did we have? We had like 1 over 1 minus 2, so that was negative 1. And then we had 2 over 1 minus 4, which is 2 over negative 3. And And what's happening here? So our numerator is going up, like indexing, and our denominator is going down. Like our denominator is becoming more and more negative. So, as our value of n increases, what's happening to our b's, we're gonna converge. So, because we're starting at like -1, and then we're getting to -2/3, and then we'll get to what? 3 over 1 minus 6 is -5, so -3/5. And then what are we gonna get? We're gonna continue going to 4 over 1 minus 8, so that's -4/7, which is still more, so these are getting closer and closer and closer. So b sub n converges. And what happens to c sub n? Well, if you recall what we were plugging in, what did we have? We had 1 over 1, so there's 1. So starting at 1. Great. And then we had 2 squared, which is 4 over 3. So we got 4/3, which is like up there. And then we had 9 over 8 minus 1 is 7. So 9/7. And then we have 16 over 15, which is like very close to 1. So what's going to be happening? Well, we can also think about like the growth rate. So like what's happening to our limit? As x approaches, oh sorry, not x, n, you can say n. As n approaches infinity of n squared over 2 to the n minus 1. Well, if you think L'Hopital on this, what are we going to get? Because it's indeterminate form, but once we can utilize L'Hopital's rule, we can say that this is going to be limit n approaches infinity of 2n over 2 to the n times natural log of 2. And that still doesn't get us very far, but then we can L'Hopital again, so we get limit as n approaches infinity of 2 over some number times 2 to the n. It's natural log of 2 squared. And that is going to give us 0. And so, since we have a limit, we know that this converges. Because we have a limit, which is a number. Alright, so here's a puzzle. Think about this puzzle. Use 1, 1, and 1 to make 6, and use any operations that you like. My suggestion is to use factorial. So pause the video, think about this puzzle. So what could you do? You could do 1 plus 1 plus 1, but then throw a factorial. So then you get 3 factorial, which is 3 times 2 times 1, and that's going to give us 6. Cool. Factorial is going to be useful. Factorials are useful in lots and lots of things. Factorials. They get crazy though. If you're trying to do factorial of a non-natural number, then you have to use the gamma function, and that's a lot. But feel free to journal about that. It sounds like fun. Alright, so squeeze theorem. If we are looking at a limit of our sequence is giving us a number, and the limit for another sequence, b, is also giving us that number, and there is an integer n, capital N, such that a sub n is less than or equal to c sub n, which is less than or equal to b sub n for all little n's greater than capital N. So if at a certain point in our counting numbers, we're getting something where we have a is down here, b is up here, and c is somewhere in between, then just like our squeeze theorem for functions, we're going to have that our limit as n approaches infinity of c sub n is going to give us the exact same thing as our limits for a and b, because they're squeezing from the top and the bottom what that value of c can be. So we got to show that this sequence converges, and we got to find its limit. So what could we do? Pause the video, think about it. So what are some options that we could use for our a sub n and b sub n functions, sequences, which would squeeze this? Well, we have this -1 to the n power, which we saw before would just kind of like change the sign. And so that's, I suppose, somewhat useful, because we get like less than or equal to's or greater than or equal to's for what a and b can be. So we can just choose like a positive value and a negative value, and we can be okay. And then we're thinking also, okay, so we have 1 over n factorial. Factorial is taking the product, the repeated product of sequentially smaller values. So what could we use to kind of like sandwich that? Well, we could use something like 1 over 2 to the n, and then positive and negative of that, or plinus of that. We could also just use good old-fashioned 1 over n, right? The reciprocal of n is not going to be, like, the reciprocal of n is not going to be any greater, is not going to be any less than the reciprocal of n factorial. Because, I mean, if you just think about the example of like 1 over 2, 1 over 3 versus 1 over 3 factorial, what's greater? The 1/3. So we can do plinus of that as well. And so we know limit as n approaches infinity of 1 over n is going to give us 0, and also plinus on these, right? And so by the squeeze theorem for sequences, we can say that this converges, and it converges to 0. So its limit is 0. So if you're taking the absolute value of your sequence, and that's going to still give you your limit 0, then you know that your non-absolute valued sequence is still going to give you a limit of 0, so you're getting conversions. And that's really helpful, which we saw like up here. Effectively, that's where that's coming from. That when we're taking pluses and minuses, but we're still finding that we have the same limit, and it's 0, then the pluses and the minuses don't make any difference, which is pretty cool. So, how can we find a sequence with these first 5 terms, and then figure out if that is going to converge or diverge? So think about the pattern. We can think about the numerator and denominator separately. Because it looks like the numerator is powers of 2, and the denominator is just odd numbers. And think about how we could write that using n's. So 2 to the n power, that can be our numerator, right? Because we have 2, 4, 8, 16, 32, so that's our powers of 2. And then our denominator, we need to be a little bit careful because we need to start at 1, but the way that we typically write like odd numbers is we take 2 times an integer, and then we add 1 to it, and that gets us an odd number, because we take an even number, add 1 to it, and you get an odd number. But when we plug in 1 here, we'll end up with 3 in the denominator, and that's not what we want. So if we can index it back just by taking an odd number and then taking taking an even number and taking away 1, then we'll get the index that we want. And so what is going to happen to this sequence? Is it going to converge or diverge? Well, if we look at the limit as n approaches infinity of this, what's going to happen? Our numerator, if we think, okay, we got indeterminate form of infinity over infinity, so we're kind of sad. But that's okay, because we can L'Hopital this, and so we'll get this is equal to limit as n approaches infinity of 2 to the n, natural log of 2 over 2. So then we get 2 to the n minus 1 times the natural log of 2, limit as n goes to infinity, just because I used exponent properties there, and what do we get? Infinity. So this sequence diverges. Because we are not getting a number. Some vocab, monotonic, or monotonicity. So we have a sequence is monotonic if its terms are not decreasing. So if it's either increasing or it's staying the same, then we have a monotonic sequence, or if its terms are non-decreasing. So if it's either staying constant or going down. Monotonicity is just thinking about like the behavior of it. So we can further specify saying, okay, we have a monotonic increasing function. So like your age is a monotonically increasing function because you are getting older all the time. But it's if you're like going on a hike up a mountain, then you could also have a monotonically increasing height, because even if you stop for a rest for a little while, you're still you're not going down until you start descending the mountain. So is a sub n, which we've been looking at a little bit already, is that going to be monotonic? No, because we're alternating between 2 and 4. How about b? And I forget what we had for b. Let me go get that. Alright, so I'll do you one better. If we're looking at b sub n, we have, in Desmos, we have x over 1 minus 2x. And so you can make like a table and then put in discrete inputs. So I took off this function, but I want you to be able to see this. So what is happening to our points? What's going on? We have -1, -0.6 repeated, -0.6, and then we'll just keep on going. So what's happening? We have a monotonic sequence because it is non-decreasing. And what about c sub n? We got n squared. So we got x squared. And then 2 to the x, 1 minus 1. And what do we end up with? We go from 1 to 1.3 repeated, and then we go down. So no, not monotonic. No. Alright. A couple more things. So we got a bounded sequence. A sequence is bounded above if there's a number, like a y value, that is greater than all of your terms in your sequence. And that's called the upper bound. Like the smallest number possible for that is going to be your upper bound. Your sequence is bounded below if there's a number, a y value, that is less than or equal to your sequence's values, and that the tightest lower bound on that is called the lower bound, that number n. And your sequence is bounded, so just bounded, if it's bounded above and below. That is boundedness. So if I'm asking you, like, is a parabola bounded? You gotta say no, because that is not bounded above, like your regular old parabola, x squared. Bounded below, yes, but is it bounded above? Absolutely not. So, if you had like n squared as your sequence, it's not bounded above, because that's going to be growing. It is, however, monotonic, because n squared for our positive integers inputs is going to be monotonic, because it's non-decreasing. Alright, so if a sequence is bounded and monotonic, then it converges. And I think that that's something that you can justify. Because if you know that it's bounded, you know that there's an upper limit and a lower limit to what those outputs can be. And if you know it's monotonic, then you know that it's either non-decreasing or non-increasing. So the convergence, I think, falls out very quickly from that. There might be a few cases that you might need to justify, but this is something definitely within the realm of something you can prove. So the question is, do these converge? Why or why not? So a sub n, oh, and we got different ones now. Whoa, wow. Changing it up. So we got a sub n is 1 over n. 1 over n is bounded, right? Because starts at 1, but then it goes to 1/2, and then it's never going to get to 0. So that's bounded. And it's also monotonic because it's non-increasing. So then, converges? Yes, by this theorem. How about n squared over n plus 1? So let's think about that. What's happening as n approaches infinity of n squared over n plus 1? Where's that going? Is it bounded? I think not. I think that this is not a bounded sequence, so it can't converge because it's not going to a number. What about c sub n? We have this just negative 1 to the n power, so that's going to alternate between negative 1 and 1. It's just going to be, well, first it's going to be negative 1, then positive 1, negative 1, positive 1, negative 1, positive 1. So yes, it's bounded, oh, but this one does not converge. Because this limit does not exist. So we have this c sub n that's going between negative 1 and positive 1. So it's bounded, yes, but it's not monotonic. And so we can't for sure say that it converges. And in fact, well, since we don't have a limit here, the limit as n approaches infinity of negative 1 to the n power, that doesn't exist. So no, this does not converge. Oh, that's it. Cool. Don't you love that limits are coming back? I love it. It's great.